This video is about our paper in NeurIPS 2019, online sampling from log-concave distributions. Our motivation comes from Bayesian statistics. Suppose we have a probabilistic model for how observations yk are generated given a parameter theta. By Bayes' rule, the posterior distribution over theta is given by the prior multiplied by the likelihoods of each of the yk. Letting these be e to the minus fk, the distribution is then given as e to the minus sum of the fk. One way to do posterior inference is to sample from this distribution. Moreover, an important challenge in scalable Bayesian inference is to do this efficiently, even when the distribution changes in response to more data yt coming in. We formalize this problem as follows. At every time t, we require an independent sample from the distribution pt proportional to e to the minus sum of fk from 0 to t, given access to the gradients of the fk. We require that the algorithm is efficient, that its time does not scale with t each update. Under natural assumptions, our algorithm based on variance-reduced stochastic gradient Langevin dynamics solves this problem in polylog t time per update. There is also a 1 over epsilon polynomial dependence in the desired accuracy epsilon. Our assumptions are satisfied in a common use case, the case of Bayesian logistic regression for IID data. Applying our theorem, we show that we can do online Bayesian logistic regression in polylog t time per update. Our theorem requires the following assumptions under ft. Firstly, that the ft are convex and L smooth, i.e. their gradients are L Lifshitz. Secondly, the distribution pt satisfies sub-exponential concentration around the mode xt star of the distribution. And finally, between t and 2t, the mode of the distribution drifts on the order of 1 over square root t. Note that the second condition is weaker than strong convexity, which is important for many applications such as logistic regression. The third condition is satisfied in the case where the data are obtained IID from some distribution. For example, you would expect the sample mean to drift by on the order of 1 over square root t between when you have t points and when you have 2t points. One standard approach to sampling from a log-concave distribution e to the minus f is Langevin dynamics, which is basically gradient descent plus Gaussian noise. However, calculating the gradient in Langevin dynamics requires evaluating the gradient of the entire sum, which takes linear time. The next natural idea is to use stochastic gradients. This is the SGLD algorithm. We take the gradient of a random fk to substitute for the gradient of the sum. However, by itself, the variance is too high, so it takes too long to converge. In fact, asymptotically, it is no better than Langevin dynamics. The solution is to use variance-reduced stochastic gradients, as in the Saga-LD algorithm. The Saga-LD algorithm is as follows. For each fk, we keep the cached gradient of fk at some past point uk. Now, at a point x, to get the next point, we will take a Langevin step with a gradient that's estimated in the following way. Instead of computing the gradient of all the fk at x, we sample a subset of size b, the batch size, from 1 to t, and we only compute the gradients of those fk at the current point x. We use these to correct the estimate from the sum of the cached gradients. Using this gradient average reduces the variance of the gradient. Finally, we update the cached gradients with the b new gradients that we computed. For the online algorithm, we carry out this procedure for each t, taking a number of steps that's poly-logarithmic in t. There are a few technical things we have to do. We have to reset the point to a previous power of 2 when it's too far away from the mode. We have to end at a random time, and we also have to force a refresh of gradients that have not been updated recently. Our proof relies on previous convergence bounds for SGLD. These bounds say that the number of steps necessary to get epsilon error is proportional to the initial squared Wasserstein distance times the variance of the stochastic gradient sigma squared over epsilon squared. Our first step is hence to bound the variance of the stochastic gradient. Ignoring log factors, we show that using variance reduction, if all samples stay within order 1 over square root t of the mode, then the variance is on the order of t. The initial squared Wasserstein distance at time t will be on the order of 1 over t, so multiplying gives that the number of steps required is on the order of a constant. Secondly, we show using a martingale exit time argument that with high probability, the samples will stay inside a ball of radius 1 over square root t around the mode. In summary, we formalized the online sampling problem for large-scale Bayesian inference. We proposed online Saga LD and proved the first almost constant time per epoch running time bounds, and we obtained competitive results for online logistic regression. You can see the paper and supplementary materials at the link tiny.cc/LMV19. Thank you.